Hey everyone, and welcome. We're about to jump into an optical illusion you have definitely seen, probably 1,000 times, but maybe you've never really thought about what's going on. Yeah, we're going to crack the code on the science of the bent straw.
You know the one, right? It's that classic little mystery. You put a perfectly straight straw into a glass of water and bam! It looks like it just snapped right at the surface. Well, it's not magic, it's physics. And trust me, by the end of this, you're going to see the world just a little bit differently.
All right, so what is actually happening here? Well, the thing that's responsible for this, it has a name, and it all boils down to one simple fact. Light doesn't always travel in a perfectly straight line. Sometimes, yeah, it takes a little detour.
Okay, let's put the official name on this. The term for it is refraction. And all it is really is what happens when light moves from one substance, like air, into another one, like water. As it crosses that boundary, its speed changes, and, this is the crucial part, it bends. And that bend is the entire secret behind the illusion. So, which way does it bend? Well, think about it like this. Imagine you're pushing a lawnmower across smooth pavement, and you hit a patch of really thick, muddy grass. The first wheel that hits the mud is going to slow down, right? And that's going to cause the whole mower to turn. Light does basically the same thing. When it goes from thin air into denser water, it slows down and bends towards an imaginary line we call the normal. Just think of it as a line straight down, perpendicular to the surface. And what happens when the light goes from water back into the air? You guessed it. It speeds up and bends away from that same line. But here's the thing. This isn't just happening randomly. Oh no. Physics loves rules. And the way light bends follows two very specific, very predictable laws. Let's break them down. Okay, so rule number one, the plain rule, is super simple. The light coming in, the light that gets bent, and that imaginary normal line, they all stay on the same flat surface. Nothing is veering off to the side. Now, rule number two, this is the real key, the ratio rule. What it means is that the relationship between the angle the light comes in at and the angle it bends to is always the same for any two materials. It's not a guess, it's a constant, totally predictable number. And this quote here, this is the fancy official way of stating that second rule, which has a name, Snell's law. Now, I know it sounds a little dense, but it's just a really precise way of saying that the amount light bends is no accident. We can actually calculate it. And that word constant in there, that's the secret sauce. And here's what that looks like as a formula. Now, don't get hung up on the math, seriously. All this is saying is that if you take the angle of the incoming light and the angle of the bent light and you do a little trig, you always get the same number for those two materials. That number is our constant. So, what do we actually call this mysterious constant? Well, that constant is so important, it gets its own name. And it's one of the most fundamental ideas in all of optics. We call it the refractive index. So just think of the refractive index, you'll usually see it as the letter N, as a kind of score. It's just a single number that tells you the bending power of a substance. Simple as that. The higher the number, the more that material slows down and bends light. Okay, so where does this score even come from? It's actually a direct comparison. It's the speed of light in a perfect vacuum, that's c, light's top speed, the universal speed limit, divided by the speed of light in whatever substance we're looking at, which is v. So the refractive index is literally telling us how much of a speed bump a material is for light compared to its absolute fastest speed. And this is the aha moment. This is where it all comes back to our straw. Because that very same number, that refractive index, it connects directly to what our eyes are seeing. It's the ratio of an object's real depth versus its apparent depth, where it looks like it is. This right here, this is the heart of the whole illusion. Let's put some real numbers on this. So a vacuum has a refractive index of exactly 1. Makes sense, right? Light isn't slowed down at all. Air is super, super close to 1. But now look at water. Its score is 1.33. And then glass is even higher, around 1.52. So just by looking at these numbers, you know that light is going to bend way more when it hits glass than when it hits water. Okay, time to put all these pieces together. Let's solve this mystery once and for all. So let's just recap the physical significance here, because it's really cool. This one single number, the refractive index, it tells us two incredibly important things. First, how much a light ray is going to bend. And second, the actual speed of light inside that substance. I mean, isn't that wild? It's such an efficient, powerful piece of information packed into one little number. And here it is, the grand finale. The solution. Light from the part of the straw that's underwater bounces off and travels towards your eye, but to get there, it has to go from the water back into the air, and right at that surface, it speeds up and it bends. Here's the catch. Your brain doesn't know about refraction. It assumes light always travels in a straight line. So your brain traces that bent light ray backwards in a straight line to a place that's shallower than where the straw actually is. It's seeing the apparent position. So the straw isn't broken at all. Your brain is just getting tricked by physics.
So the next time you're looking at a fish in a pond and it seems way closer than you know it is, or you see that shimmering heat haze on a long road in the summer, you'll know exactly what's going on. It's not a trick of the mind. It's just the beautiful, predictable physics of light taking a little detour. Now that you know the secret, what other everyday illusions are you going to be able to explain?